Awesome, thanks. So I would like to thank Stamatis and Iulia for their amazing introduction to my topic. And please, Maria, let me know if there is some annoying background. I will try to close the window or turn off the fan.
Okay, for now it's fine.
Okay, yeah, sure. So, hi everyone, my name is Dimitris Kantzas and I'm a PhD candidate at the University of Amsterdam. I'm working under the supervision of Professor Sarah Markov, and today I would like to talk to you about how we can further understand galactic jets launched by stellar black holes in X-ray binaries, or in simple words, what Iulia and Stamatis were talking about, but for their smallest and slowest siblings. Just to be sure that everyone is at the same page, stellar black holes located in X-ray binaries accrete matter through an accretion disk from their companion star, and they launch two mildly relativistic jets during outbursts, as you can see here in this artist's impression. These jets carry away material and energy from the very close vicinity of the black hole to the outer regions of the black hole binary, and they affect their medium. As you can see on the right-hand side, where you can see the radio image of Cygnus X1, a very popular black hole X-ray binary, where the binary is located down here. And if we zoom in this region, you can see the radio jets that are launched, and due to their interactions with the ambient medium, they create this very beautiful bow shock, which is unique in the sense that we haven't really detected any other X-ray binary producing this very unique feature, this bow shock. In fact, we can use this bow shock to extract useful information, such as the power carried away by the jets, or eventually what's the composition of the jets. But in case you're wondering why to study X-ray binaries, and in particular X-ray binary jets, it's because we want to understand some fundamental physical laws, such as accretion, in particular around compact objects like black holes. We moreover want to understand the nature of X-ray binaries, those X-ray binaries that are eventually the gravitational wave signals, are the progenitors of gravitational waves. And we can actually use the X-ray binaries located in our own Milky Way or the nearby galaxies to extract useful information about those X-ray binaries that eventually will collide in these very distant galaxies. Finally, there might be some very interesting connection between galactic X-ray binary jets and galactic cosmic ray sources. So, cosmic rays are elementary charged particles that accelerate in some yet unknown sources to high energy. And in particular for galactic cosmic rays, these particles may gain energy of the order of PeV, namely 10 to 15 eV. These sources are known as pevatrons. So these PeV particles escape the source, they propagate the Milky Way, but they are deflected due to their magnetic field. So when we detect them here on Earth, we cannot really track back to find their origin. A very robust way to identify these pevatrons is by studying the gamma ray counterpart. In particular, leptonic cosmic rays, electrons, will produce gamma rays of the order of TeV, hundreds of TeV, or even PeV, due to leptonic processes, such as inverse Compton scattering. But for the case of protons, they will produce gamma rays as a result of photopion or proton-proton interactions, but they will also produce this smoking gun known as neutrino. In fact, a couple of months ago, the LASSO experiment released a very short catalog of TeV to PeV gamma ray sources, galactic gamma ray sources. 10 of them are unidentified. So my question is, can these unidentified sources be galactic jets launched by stellar black holes? Or in other words, are jets launched by black holes pevatrons? To be able to answer to this question, I have developed a leptohadronic multi-zone jet model. that takes into account both leptonic and hadronic processes. Just to give you a very brief overview of this model, I assume that there is a jet that is launched at some position very close to the black hole, and it propagates outwards. At some particular distance from the black hole, particle acceleration kicks in, which means that the accelerated particles now follow a power law in energy. For the accelerated population of electrons, I take into account zero neutron radiation and any inverse Compton scattering with multiple targets. And the accelerated protons interact with the jet flow and the jet radiation to give rise to secondary particles, such as muons and pions, and eventually neutrinos. For any case, regardless of the proton acceleration, I assume that there is one electron per proton in the jets, or in other words, the number density of electrons and protons is equal. Now, for every jet segment, I'm solving the steady state of the transport equation to keep track of the number density of every population in the jets. I first use this model to a canonical high mass X-ray binary, high mass in the sense that the companion is of high mass. And in particular, I'm using the study case of Cygnus X1. Cygnus X1 is a very unique source. I, for instance, showed earlier the Bosov, but also it shows some persistent jet emission, and it has some relatively well-constrained dynamical quantities. For instance, with the VLBA technique that we heard earlier, they have derived the exact distance of this source from the Earth, which is of the order of 2.2 kiloparsec, which eventually leads to a quite well constraint of the mass of the black hole, which is of the order of 21 solar masses, quite heavier compared to what was thought earlier. There are two very interesting features in the SED of this particular source. The first one is that the integral collaboration has announced some MEV linear polarization of the order of 70%, which is a hint for single-neutron radiation coming from structured jets, coming from structured magnetic fields, which is the jets. And finally, Cygnus X1 is among the very few X-ray binaries that has been detected in the GeV band. So taking all this into account and also using the very first ever simultaneous radio to X-ray dataset obtained by the Chalkbox campaign, which is an observation of Cygnus X1 for a whole orbit, I'm searching for the best fit of this model. So here in particular, I'm showing the energy flux as a function of the photon frequency and what are the different physical processes. So first of all, the outer regions of the jets contribute via single-neutron radiation in the radio band. Now, to explain the MEV, the polarized MEV flux, that has to be single-neutron radiation, but coming from a different region from the jets, and in particular, it's the particle acceleration region. And the best fit value for this region is of the order of 80 gravitational radii from the black hole. The companion of this binary system dominates in the optical, and I'm really looking forward to listening to a talk later this evening, what is a corona from X-ray binaries, but in my jet-oriented model, and to be able to explain the whole X-ray spectrum, I require the simplest corona ever, which is a thermal plasma of electrons that upscatters the disk photons in the X-ray band. Now, it's very interesting that you see, for instance, we saw a few times the Marser model earlier in this session, and the need of multi-zones or different segments in the jets. We'll listen another talk later, but you can also see it here So just to remind you, the radio is coming from the outer regions, and the polarized MEV might originate in the, let's call it, very close regions of the black hole, of the jets. But to be able to connect these jets to a potential pevatron, we have to go to the dvtotv spectrum, which I'm plotting here. So once more, I'm showing the energy flux as a function of the photon frequency. And the accelerated electrons in the jets that produce these MEV synchrotron photons will eventually upscatter these MEV photons in the GeV band that are detected by Fermi. But what's the role of the accelerated protons? You can see it here. So the accelerated protons interact with these MEV photons to give rise to these TVXs. Now, future facilities like the Cherenkov telescope array, for which I'm plotting the sensitivity here in blue, will be able, as you can see, to detect such a potential TV emission coming from the jets of Cygnus X1, which is a hint for a galactic pevatron. So what I want you to remember from this exercise is that protons can indeed accelerate up to 1 PeV. And if this is true, then there will be some TV emission that can only be of hadronic origin, which is a hint for a galactic pevatron. But I further applied this model to a prototypical low mass X-ray binary, which is that the companion is of low mass. And in particular, I'm using the prototypical study case of GX339-4, which is almost a boring source because it goes into outbursts every 2 to 3 years that last for a few weeks, although the past few outbursts were failed. And there was a very bright outburst back in 2010 that is worth revisiting its spectral energy distribution, although there is one caveat with this source, which is its distance. It's of the order of 8 kiloparsec, and it's not very well constrained anyway. So following the same process, I'm using this 2010 outburst spectrum to find the best fit. So I'm plotting once more the energy flux as a function of the photon frequency. And as you can see once more, the outer regions of the jet dominate via synchrotron radiation in the radio up to the infrared. And there might be some polarized MEV jet synchrotron flux from the particle acceleration region, which has not been detected yet. There is some very interesting physics in the jets of GX39-4. Please ask me later. I don't want to go into details, but it's about these optical emission here. And once more, to explain the X-ray spectrum, I require the simplest ever corona, namely this thermal electron plasma that upscatters the disk photons. Now, once more, trying to connect these jets to a potential pevatron, I have to go to the dvtotv gamma ray spectrum, which I'm plotting here. So once more, you are seeing the energy flux as a function of the photon frequency. The accelerated electrons produce some MEV photons that are upscattered in the GeV band, and the accelerated protons interact with these photons, I mean the MEV photons, to give rise to this excess here, which unfortunately is way below the CTA sensitivity. Even if I assume the maximum available power to the accelerated protons. As I said in the beginning, there is this connection between gamma rays, but neutrinos as well, especially to hint for a pevatron. So the next step is to find the self-consistent neutrino spectra, in particular of Cygnus X1, because the other source you saw there's no really anything interesting. So what I'm plotting here is the energy flux of neutrinos this time as a function of the neutrino energy. And I'm comparing my predicted flux, which you can see here in this black weird line, to the upper limits of ice cube, which are all these orange, green, blue lines. So the predicted flux remains below the ice cube upper limits. And because I don't really understand anything from this comparison, I wanted to compare the neutrino rate. And I found that for ice cube in particular, there might be a rate of 0.7 muon neutrinos per year when the jets of Cygnus X1 are over there. And for future facilities like
KM, you have 5 more minutes.
Really?
Yeah, you entered the time of 4 questions.
Ah, okay, yeah, okay. Yes. I don't need 5 more minutes. Okay. I'm done. And in the case of future facilities like KM3net, there might be an increase to 0.09 muon neutrinos per year. So yeah, literally that's my conclusion. So what I tried to convey in this talk is that perhaps galactic jets are these missing pevatrons, or in other words, they can accelerate PV cosmic rays. And to be able to answer to this question, I developed this leptohadronic jet model and applied it to the very first ever simultaneous radio to X-ray spectrum of Cygnus X1. And I found that there might be some TeV emission that can only be of hadronic origin. And then I also applied the same model to GX39-4, but unfortunately, even CTA will not be able to detect. And looking forward to some neutrino results. So thank you very much for your time. Sorry if I was over.
Thank you, Dimitris, for this very interesting talk. And we have still time for questions, so plenty of time, I would say. So if someone wants to ask Dimitris a question, please do so. Let's see. I don't see any raised hands. Okay, let's see the chat. I see one comment by Dimitris Papadopoulos, who said, very interesting talk. I would like to know more. I don't know if this applies to your or the previous talk. Okay. So I have a question, Dimitris, that I might have missed. It was about the last slide you had with the comparison of the neutrino spectra.
Sure.
Yes, here. So I see one other model that the red line, which corresponds to this model, applied to a 24-hour flare or something like this. Mm-hmm. As far as I understood, your model is steady state, so you compute the steady state emission. Do you have any plans of computing also outbursts or modify your code somehow to model this type of flares, which I'm not aware of? Yeah.
Yeah, so that's a great point. In fact, it will be quite difficult to just modify the current version of the code to try to examine flares. But with some further modification, I would be super interested in searching and examining the time dependence. But it's not in the very, very, very close plans, let's say.
I see. And one more comment, because you mentioned about Cygnus X1 and this impact that it has on its environment, and we see this boson structure and everything like that. Mm-hmm. Have you considered also what happens to the escaping cosmic rays from this jet? So do you have any plans in looking into the propagation of cosmic rays into the environment of these XRBs?
Yeah, I don't know if you can foresee the future. So that's the obvious next step, to try to understand how cosmic rays escape these sources and propagate in our Milky Way, so as not only to study, so this is the point-like source, right? So this is the intrinsic neutrino flux emission. But I would also like to see how and if these X-ray binaries can contribute to the diffusive neutrino emission. for which I have to take into account the cosmic ray propagation and how they escape from these jets.
Okay, I will be looking forward to that. And I see also one more question so that I do not monopolize the discussion by Dimitris Papadopoulos. So, Dimitri, I see that you have your hand raised.
Unmute. It's okay now?
Yes, now we can see you.
Okay. Dimitri did very nice, very nice talk. Well, I'm trying to do something around this area recently, but my question is, if you have that jet, don't you think that you would change the momentum of the black hole, would change also the quadrupole moment? How do all these effects affect all these measurements that we are doing? You know, the process by Blanford and Janek is telling us that something like that you are looking at creates a transfer of momentum from the black hole outside. What do you think? Can you change all your results?
Yeah, I mean, perhaps I can just make a very short comment because this is a huge area.
Okay.
I would say that at this moment, this jet model is quite simplified in that way, in the sense that it's not really tied to the accretion or the jet launching mechanism. So I'm not distinguishing between Blanford-Nyack or Blanford-Payne, but of course, one way or the other would alter the jet dynamics that eventually change these results. Yeah, for sure.
Okay. Okay, thank you. Thank you.
Thank you.